All right, welcome to this explainer. Today, we're going to absolutely deconstruct the architectural decisions you need to make to build resilient, enterprise-grade AI systems. We are officially leaving those brittle prototype-style wrappers in the past. Let's dive right in.
So let me ask you a question right off the bat. Is your AI architecture built on a massive single point of failure? Because, a lot of modern deployments are essentially just monolithic wrappers built tightly around a single large language model from one specific provider. And think about what that actually means in production. If that provider experiences an unexpected outage, or hey, if they suddenly decide to jack up their pricing, your entire enterprise application is just completely at their mercy. That's a single point of failure that a real production-grade system simply cannot afford.
To figure out how to solve this, we're going to tear down a hypothetical but very realistic AI-powered enterprise supply chain orchestrator today. The old way of doing things, that single provider monolith on the left, suffers from terrible vendor lock-in. It's totally limited by the context window of just one model, and frankly, it's incredibly brittle. But the modern architectural shift? That's all about building a model-agnostic ecosystem. This new approach is composable, it uses clever proxy routing, and it leverages a deeply resilient multi-agent graph. Let's actually break down exactly how you build this ecosystem layer by layer.
Starting right at the foundation, Layer 1, the AI abstraction imperative.
The fix here is something called a proxy router. Instead of your team hard-coding separate, messy API integrations for every single model out there, like, one for Claude, one for Gemini, another one for GPT, an abstraction proxy layer standardizes the whole handshake. Your core application code only talks to one single unified endpoint. The proxy completely handles the translation and routing behind the scenes. This is a total game changer because it completely removes the risk of vendor lock-in right out of the gate.
And the true power of this abstraction layer is pretty much instantaneous. When you aren't chained to one provider, you unlock the ability to dynamically switch models on the fly. Say a provider goes down? No problem. Your system automatically routes to an alternative, and the end user never even notices a blip. It also centralizes your token economics into a single dashboard. But maybe most importantly, you get real-time benchmarking. You can evaluate models on the fly to find that perfect, absolute sweet spot between speed and quality for any specific task.
To put that into perspective, look at how our supply chain orchestrator manages different workloads. If it just needs to rip basic shipping coordinates out of a database, well, that needs high speed and low cost, right? The proxy automatically routes that specific task to an incredibly fast, lightweight model. But if a user uploads a dense, 50-page supplier contract for risk analysis, well, that requires deep context and serious reasoning. The proxy immediately detects this and routes it over to a heavy, reasoning-focused model. So you're optimizing your system latency and your enterprise budget both at the exact same time.
Moving further up the stack, we hit Layer 2, orchestrating graph-based agent systems. Now this represents a massive paradigm shift in how we build. Linear chaining, which is how everyone built early AI apps, is sequential, it's rigid, and it's strictly step-by-step. If step 2 fails, the whole chain shatters. Modern systems, though, leverage graph-based orchestration using frameworks like LangGraph. With LangGraph, we aren't just chaining prompts, we're building highly dynamic systems where specialized AI agents collaborate. They evaluate conditions, they branch logic, and they hand off tasks dynamically based on what's actually happening in the workflow. It's how you get reliable, multi-step enterprise solutions.
Let's see this graph orchestration in action. Say a single disruption alert hits our supply chain system. It cascades through a specialized graph of agents. Step 1. A triage agent detects a disrupted shipping route in the Red Sea. It instantly hands off to Step 2, a routing agent, which evaluates the business impact. Then, Step 3, a specialized logistics agent, which is powered by a super-fast LLM, rapidly proposes 3 alternate routes. Finally, Step 4, a risk agent, powered by a heavy, deep reasoning LLM, audits those exact new routes for legal and customs compliance. It's a beautiful thing. Different models handling the specific tasks they're uniquely designed for.
Which brings us nicely to Layer 3, architecting AI memory systems.
Here's the thing. Large language models don't natively remember you. When you close the session, they forget everything. So engineers have to explicitly design the balance between 2 completely distinct types of memory. Short-term, or session memory, is driven by the active context window during a live interaction. Contrast that with long-term persistent memory. That's where we convert massive troves of enterprise data into mathematical vectors, store them in vector databases, and use retrieval-augmented generation, or RAG, to pull exactly what we need into the model's brain exactly when it needs it.
But designing this memory architecture is all about balancing some pretty harsh trade-offs.
Like, if you try to just shove 5 years of supply chain history into the short-term context window, you get severe context window bloat. The AI gets confused, reasoning speed absolutely tanks, and your token consumption goes through the roof. On the flip side, relying purely on long-term memory introduces latency from converting text to embeddings, and you run into the mathematical limits of retrieving data using Euclidean distance. You have to aggressively, and I mean aggressively, manage what stays in the active session versus what lives in the database.
Because at the end of the day, token economics dictate your memory architecture. Period. Generated output tokens are significantly more expensive than the input tokens you're feeding into the model. If your context window is bloated with a bunch of irrelevant memories, the model spends way more computational power reasoning through it, which inevitably drives up the cost of the output generation. Proper, strict memory management is literally how you protect the financial viability of your AI system.
Finally, right at the very top of our architecture, we reach Layer 4, System Messages as Model Governance. We need to fundamentally reframe how we view the system prompt. It is definitely not just a place to define a cute persona or politely ask the AI to be helpful. No, in an enterprise architecture, the system prompt is the absolute deterministic firewall. It is the core governance layer that forces responsible AI behavior and lays down strict operational rules.
Look at the hierarchy here. The user message on the left, that is pure variable input. It's unpredictable, it's chaotic, and it's exactly where prompt injections originate. But above that sits the system message. This is your static behavioral definition. It holds absolute priority, and it silently appends your safety guardrails, your operational constraints, and your formatting rules to every single request. It ensures that no matter how crazy the user input gets, it never overrides your core architecture.
So for our supply chain orchestrator, that enterprise-grade system message is highly engineered. We're talking strict role boundaries, literally explicitly forbidding the AI from answering non-logistical questions. No writing poetry on company time. It forces structured output formats, like JSON, so the rest of your software stack can actually read it. It embeds few-shot reasoning examples to guide the model's logic. And crucially, it sets up hard stop conditions and fallback protocols to completely shut down hallucinations when the AI hits data it doesn't understand.
So what does this all mean when you put it together? When we purposefully architect abstraction layers to kill vendor lock-in, when we build out collaborative, graph-based agents, when we carefully balance the massive trade-offs of session and persistent memory, and when we enforce strict system-level governance, we actually evolve. We stop building brittle little wrappers around consumer chatbots, and we start building true, resilient enterprise software that can handle mission-critical operations.
I'll leave you with this provocative thought. The tools, the frameworks, and the architectural patterns to build these highly resilient, composable AI ecosystems, they exist right now. So if your primary LLM provider suffers a catastrophic outage tomorrow morning, is your technical stack designed to seamlessly adapt, or is it going to completely collapse? The architecture choices you make today will determine that answer. Keep building, keep learning, and thank you for joining me on this explainer.